Those stupid moon hoaxers really get to me sometimes. It's not just the fact that they're so stupidly, pathetically wrong. It's not even that they're so smug, superior, and self-righteous over what they think is a great find that not even the best scientists in the world were able to uncover. It's mostly because they continually assault me with their idiocy, lie about me on my channel and other places, and generally just don't leave people in peace when they've been thoroughly trounced. Since ignoring them obviously won't cause them to go away, all I know to do is expose how completely moronic they are, although they won't even see it.
Looking at the Apollo 15 moon flag waving video, and there has been much debate about this video, what it truly shows. And I was looking at this, and I'll tell you, I personally didn't think much about the flag on the moon showing much of anything or proving anything. But as I was watching this video, it struck me that there is something in this video, in the physics of the flag movement, that can prove whether or not this flag is on the Earth or on the moon. And that something is the fact that the flag is displaying a physical property known as simple harmonic motion. It is displaying periodicity. And by just taking some simple measurements, we can actually calculate the acceleration of gravity where this flag is at. the flag pulls towards him. Okay. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But then we have our equation. T is the periodicity of the pendulum. Now, the flag on the moon is like a pendulum. It's really not quite like this simple pendulum, but we're going to start off with this. Very simple. We have the periodicity here, the time of the period, and we have the length of the pendulum. In this case, it would be the part of the flag that hangs down would be a pendulum, and then we have g as the acceleration of gravity. So this is a very simple equation to. It's actually an approximation of the true situation, but so what's the length of our pendulum? In meters, it would be about 0.9 meters. That's slightly less than 36 inches, 3 feet. And that would take into account a little bit of material that was used for the hem on top. So it was very close to the true length. Now, what's the acceleration of gravity? Let's work just the opposite. We already know that we got a period of 2 seconds. If you remember, the acceleration of gravity for the Earth is 9.8 meters per second per second. Okay, so let's calculate what would be the pendulum, the period of the flag, if it was an ideal pendulum situation, which it's not. It would be 1.90 seconds, very close to 2 seconds. Like, and this is the Earth now. Remember. We can go to a rod pendulum. The rod pendulum. This would be like the flag on the moon, or on the Earth. The mass is evenly distributed along its length, part hanging down. You know, another interesting thing about these formulas, you'll notice that the mass, it doesn't really matter what the mass of the flag or the pendulum is. That pretty much cancels out. It can be very low mass or very high mass. You get the same periodic motion. However, there are some effects of friction that need to be taken into account as you get to low masses, which I'll talk about. So here's our equation for a rod pendulum, which is essentially what the flag is: uniform density along its length. 2 pi times the square root of 2 times the length over 3 times the acceleration of gravity. So let's plug in what we know. Pendulum length. Now this is in centimeters now, so it'd be 90 centimeters. And the acceleration of gravity, once again, for the Earth, 9.8. What would be what's our pendulum period going to be for when we take into account uniform density? Well, it's less. It was 1.9. Now we're down to about 1.6. Right, compared to a period of about 1.9 for a simple pendulum. So this pendulum would actually be 1.6 seconds. which is what it should be on the Earth. Now let's take a look on the moon here. What's the acceleration of gravity on the moon? 1.622. So what would it be on the moon? Almost 4 seconds. For a simple pendulum, it'd be almost 5 seconds. So, you know, we're only getting 2 seconds. The flag on the moon in the Apollo 15 video is only showing us 2 seconds. So you know, this is showing us that the flag is on the Earth. What's nice about this is if you throw this around, you kind of see, and this is how the flag acts in all the videos on the moon. The flag acts like this. Pretty much how it would, because this is Earth. This is Earth now, so I don't think anybody's really asked the question, how would the flag actually act on the moon? Well, here's the moon right here. A little bit less friction. Well, there's going to be less friction on the moon, although there's enough. The bending and flexing of the material will slow the flag down. It doesn't go forever. It's going to slow down, so we can say probably something like this. And once again, a simple pendulum. What's this going to look like on the moon? Okay, the astronaut kind of whips the flag as he's trying to put it into the ground. I mean, does that look like what we see in those videos? This is what the flag, the moon flag, really should look like on the moon. Is this what we see? No, we don't see this. I mean, the flag should look like it's in slow motion on the moon, and it does not look like that.